I'm gonna build it. Unless you're sitting next to it, it's not gonna go.
Now, we're not vegan here on For those of you who are wondering, we're waiting for the last committee member, Professor Wakeland, because we cannot start unless the entire committee's here. So that's why we're in a holding pattern.
Bring your paper?
Huh?
Did you bring your papers? No?
What papers?
You said you published some papers?
Oh, I can.
You didn't bring them?
I can print them really quick.
Wait, yeah, you should do that.
All right.
Yeah, print a set for.
Might as well. Can you print the overheads as well?
Print the what?
Overheads.
Don't you have a copy of the overheads?
No.
You don't have a copy? Oh, really? You didn't print out copies of the overheads? Aren't they?
What are overheads? The
What are
slides?
these?
Yeah, I
You
made
didn't get
2
one of
copies.
these?
I didn't get them, so where?
Oh, I made 2
Oh,
copies.
there he is.
Oh,
Sorry about that. I'm not as fast getting across campus as I used to be.
Okay, let me email it back.
This is the latest?
Of course. Oh, no, it's an earlier edition from 6 months ago.
I don't know. It could be the same as before.
I
mean, is it the same or is it
probably,
like? I mean, this is what?
So this is the older version.
Okay.
This is for you.
Thank you.
And then yeah, I had 2 copies of the thesis and 2 copies of yes, you have one. So let me print some more.
Do you want a copy of these?
Is there an extra copy? I don't need it if it's the only copy. I can just follow on.
Oh, okay.
I'll make notes on the document because I kind of.
Okay. All right, so I guess we can start. I'd like to welcome you all to Michael's PhD dissertation defense. I'd like to introduce the members of his dissertation committee. I'm the PhD advisor for Michael, Professor Garrison Greenwood. This is Professor Tomersky down there at the end, Prokowski right here, and Professor Wakeland there from the System Science Department. We have to have a professor from outside the ECE department as a member of the committee, and Professor Wakeland is serving in that capacity. So, Michael, whenever you're ready.
All right. Well, hello again, everyone. I will present you my dissertation here. First of all, we're also streaming for people who cannot be here for different reasons, like being in a different time zone. So just to let you know. And the topic of the dissertation is a multi-agent system for adaptive control of a flapping wing micro-air vehicle. When I timed this presentation, it ran around an hour, so I tried to cut some of the introduction material and some of the background topics that the committee members are probably familiar, just to get to the 45 minutes, and then we have more time for questions. If you have questions, ask during the presentation, but also when you need when you want to ask about something, just go ahead. There'll be also time to ask questions afterwards. So I'll just move on. So not surprisingly, we'll start with introduction. So we should say, what is the flapping wing micro-air vehicle? And first of all, it's a biomimetic vehicle. That means the idea is we're looking at nature. We get inspired by flies and by bees, because those tiny insects, they have only one pair of wings, but they can achieve full 6 degrees of freedom movement, and they're very small, very agile, and very, very fast. So we look at them and it's well, can we do something similar and achieve the same properties for a robot? And other thing is, if we want to apply these kind of small robots in practice, there are some requirements we want. And first of all, we want some kind of autonomous operation. So that means there's no pilot behind each of these robots, because they'll be infeasible in case you start swarming or have some kind of massive application you want these robots to, work functional but by themselves. And another property is navigation in constrained environment, because we want it to operate. Thanks, Becky. Yeah.
Oh, thank you.
We want them to operate indoors in some kind of cluttered environment. So this is an important feature. And we also require fault tolerance, because in case there's a damage of a wing or some kind of other problem, we need to make this vehicle be able to recover and continue its mission. So what are the applications? First of all, I would say search and rescue in case of imagine in case of some kind of environmental disaster. First responders arrive to the facility. It can be like a chemical plant or something, and they want to send these vehicles to go inside a building and see what's the status of the building. Is it stable? Is it safe to go in? Are there any toxic materials present? And all of this can happen automatically without anybody stepping in and being potentially in a dangerous situation. Another situation, firemen, similar story. If you have like a building on fire, you can send these robots in and assess, what's going inside without putting people at risk. Another big area is reconnaissance and monitoring. So first, in military situation, you want to see with this robot, what's going around you, where's the enemy, what's kind of, situation going on there. And then for monitoring, that's typically for law enforcement. You want to see, again, behind the door, what's the suspect doing, and so on. So those two are fairly, not surprising, but the last one I want to mention is artificial pollination. And the idea here is, if for some reason we're in a situation we need more pollinators for our crops, and there's no bees or other ways how to do that, we could use these tiny robots potentially to pollinate the plants. And you might ask why we not use just quadcopters or some other drone for the same thing. And the problem is you can go only so small with the quadcopter technology, because you need motors, you need propellers, and that stuff just doesn't scale well after a certain point. Because after a certain point, the aerodynamics doesn't work the same way, and the motors cannot be much smaller than they are. So basically, if you want to go truly insect size and be able to operate on that small scale, you have to use flapping wing vehicles. There's really no way how you can make the quadcopter that small. And so I would like to briefly mention the expected research outcomes. So first, we need to understand if a multi-agent system is a good option for the control of such vehicle. Then we need to develop this system, this multi-agent system, and because we want the vehicle to be autonomous, we want it to be able to follow a trajectory we specify, and then we develop a fault detection and fault recovery mechanism. So we add this property of fault tolerance, and then this kind of overarching goal is to develop a vehicle that is autonomous, can follow the trajectory and can recover from a fault. So now some background information. Some of it may be familiar for you, some of it may be new, so I just go kind of briefly. So this is a model of the vehicle. You can see we have two wings. They can move certain angle back and forth, and they have some angle of attack alpha. So basically they're like on a hinge, and the wing is kind of loosely on the hinge, and then it moves forward. It moves until it stops at the angle alpha, and then it moves backwards, and it stops the same way, just in the opposite direction. So this is like a conceptual vehicle. Now I have to talk a little bit about what kind of actuators I can use for such a robot. First one is called piezoelectric oscillator. It's basically two slices of piezoelectric material, and when I apply voltage across them, it will bend either one way or other way depending on positive negative voltage. Here in this picture you can see here we have the vehicle, this is the actuator, and then it's extended and connected to transmission that then translates the bending movement to flapping of the wings. And you can see that it can be achieved to be truly insect size.
Can I ask you, where do you apply the voltage in that device?
So you have, you see tiny wires here, and basically one goes on so there are two layers of this piezoelectric material, and so you apply, let's say, positive here, negative here, or the other way around.
Just down the bottom of that structure.
Oh yeah, I think this is where you apply. This is like where it connects to.
What kind of battery for this?
Sorry?
What kind of battery?
So right now this vehicle is externally powered, and I get in a second to why. The reason is you need relatively high voltage, of like 150 volts at least. So that's fairly yeah. So right now it's only external powered, but it has good lift to weight ratio, so you can actually achieve free flight, and it allows you to go really insect size. So it's like a really tiny vehicle. The problem besides the power requirements is that it has to be driven at resonant frequency because of the inertia of the wings. So in short, if you want this to truly work and provide sufficient lift, you're like constrained to specific frequency. So you don't have, as a designer, you don't have much play in this sense. And another disadvantage is that these oscillators are only available if you at MIT Robotics Lab. If you're not, then it's really hard to get these.
So it's basically an AC waveform. Is it sinusoidal?
Yes, it's a sinusoid.
Sinusoidal, purely sinusoidal.
And
is the model basically of this device is a capacitor basically? You think? Because there's no really, it's only an AC current flowing through it.
honestly, I'm not sure. I don't think you need necessarily a mod like.
Well, it must act. You know, it's one of these basic.
Sure.
elements,
Yeah. Yeah, I guess capacitor would be reasonable. Yeah, and you can like feed it with a sinusoid, and then you can do like phase shift or offset the voltage to get it to do different things. So if you happen to not be at MIT, you essentially have to use DC motors for these vehicles. The typical scheme here is we have a motor with a gearbox with planetary gears to provide sufficient reduction. So we have enough torque at the output shaft. Then we have some kind of transmission or linkage going from the output of the motor to the wings. So we translate the rotational motion into flapping motion. And the wings itself, they are made from carbon fiber. They are carbon fiber spars. And then we have some kind of either Kapton or different plastic, thin plastic foil as the main part of the wing. Here you can see this is a robot. Here are the motors, and again there's transmission on top of it, and then here's the shaft, and it's connected with linkages to the wing. So as the motor rotates, it makes the wing move back and forth. And I have a video to show this. So let's see how this will go. Yes, so this is when it's operating. This is basically when the robot is in action. And then the assembled robot is here. So DC motors, comparatively affordable, easy to use. They don't produce as much lift, so you're restricted how small you can go and how light. But the majority of the vehicles currently available, or like currently developed, uses the DC motors. So then subsumption architecture, it's an important part of our solution. Just briefly, it's a concept widely used in robotics, that I can decompose the behavior into several layers, and they have different priorities. Every higher layer has a higher priority, and if it needs to, it can take over the lower layers. So if I make a short example, here I have some outputs from the sensors, so inputs from the sensors, then I have different levels of behaviors, and then I have actuators. And level 1 is for let's say example, a ground robot. So level 1 or level 0 will be just go straight. It's like a simple behavior, if nothing else, just go straight. Then I have level 1 behavior, which says if you find an obstacle, turn right to avoid it, because I don't want the robot to hit the wall. And then I have level 2, which is if low voltage and battery stop. And so basically the robot will go straight until it gets close to the wall, and it will turn right, and it will continue doing so until it runs low on battery. And the idea is that you can compose relatively sophisticated behavior with these very simple components, because you can easily extend it to be, if something happens, return to the base. If you identify some kind of target, do something. So it allows you to easily build up the complex behavior. And as an example, it was used in this Roomba robot. It's based on subsumption architecture. And also they use subsumption architecture on like a Mars rover in a certain extent. So it's a fairly common theme. Then just briefly about evolutionary algorithms, again inspired by nature. In short, what I'm trying to do, I have some population of individuals. Each of them represents some solution. I assign them fitness based on some function, and then I'm basically let them compete with each other and produce offsprings, and only the most fit will propagate in time, and then I'm hopefully getting the fittest at the end. So I might not get the optimal solution, but I get some reasonably good solution. Here's just a simple algorithm. I will skip it for the time being. So now we're getting to the problem definition. So far everything clear?
Well, you missed I didn't get the definition for extrinsic and intrinsic.
Okay, so the extrinsic means that in case of a robot, the extrinsic evolution runs on some kind of model. I define a model, and then I run the evolutionary algorithm, but the fitness is assigned based on this model. But intrinsic means I actually run the algorithm I evaluate it on the actual hardware. So instead of having a model of a robot, I run it on a robot and see, let's say, how fast it is or how good it is. All right, so problem definition. So we have two wings, and each wing has two parameters. One is the wing beating frequency, omega, and the other one is delta. Delta says how much I impede or advance the downstroke compared to upstroke. Because the idea is if you move the wing symmetrically, right, one way, the other way, you produce force each way you go, and then those two cancel each other. So basically, then only force you produce is the lift, and that's it. But if you happen to go, let's say, fast and then slow on the downstroke, you generate more force in one direction than the other one, and it creates momentum that turns the vehicle around. Or basically that's a simple idea. So then what I can do is, this is just a formal definition of the same, because I describe my wing motion as a cosine function, and delta is just a frequency shift, essentially, phase shift. So I'm moving it a little bit before or after the actual symmetrical movement. I will use this concept for controlling the vehicle, because if I want to turn around, I have to do upstroke faster than a downstroke, and then vice versa for turning the other direction. I'll get to that more later. Now I want to show the experimental setup a little bit. So for our experiments, we locked the vehicle to 3 degrees of freedom, which means we put it on 2-dimensional surface, on a water surface, and then the vehicle can rotate around its own axis. And the reason for this is twofold. First is to have a proof of concept that our solution works, that the algorithm works, and that the multi-agent system can perform well. And the second one is the limitation of the hardware, that currently the hardware doesn't produce enough lift to actually take off. So we were locked to this 3 degrees of freedom test plan. You can see.
Just as a comment, that water tank in the NEAR lab, which is used to do underwater sound testing, you have to have a large water tank. And that's where we got that water tank from. So the thing is, I don't know, half the size of this table. So it's a fairly good size water tank, and we would just fill it up and let it float on the surface of the water.
And they were nice enough to let us use it, so that was good. We put a camera on top, which you can see here on the left top view.
How far was the camera?
Around, it was actually on the ceiling, so 1.5 meters from the top. Like, imagine this is the water, right? So then it was on the ceiling. So I guess, yeah.
And how big was the scalar markers? Like 1 centimeter?
Like this.
Or like this, okay.
So then, yeah, and we had 3 markers, so you can determine the position and the orientation of the robot. And you can see on the right, this is a close-up view. And I happen to have a video that should present better the experimental setup. So let's see.
And you will tell what software you use to find the scalar markers? You will tell us?
Yeah, I'm using OpenCV.
Okay.
Hi, my name is Michael, and I will show you mapping the robot that is a part of the research here. So this is the robot. It is a floating platform. Here we can see the wings. This is the right wing, and you can see it's slightly smaller because I cut off the tip of the wing to test the fall detection and recovery. And this is the original left wing. You can see the wings can move freely, and then as the motor moves, it flaps with the wing, and it can go faster, slower, backwards, and so on. Then these yellow things are markers for the computer vision, so the camera can tell where the device is in the water tank. And then underneath this whole platform, we have the electronics. You can see here, there's like a battery, power distribution board, and the gum sticks over the computer. So this is the experimental setup we have here.
That's in the water lab with the
Communicate
water tank.
with the robot. Behind me is the water tank where the experiment is conducted, and here is the robot.
You can see the camera on the ceiling.
Here is a camera that captures the whole experiment, and here is a Wi-Fi router that takes care of the communication between the robot and the computer. Now, if I want to start the experiment, I have to connect to the robot over Wi-Fi. I will do it right now. And now I will initiate the wings.
It takes around 30 seconds to initialize all the
whole procedure takes
stuff.
around 30 seconds. You can see that the low-level controller has to go through all the steps, make sure everything's working correctly, and then it is able to respond to API calls from the higher-level controller that we developed. Right now we can see that the robot is following a waypoint that is on the opposite side of the water tank. And now I'll show you the graph graphic user interface, which is right here. So it says turn right and follow the waypoint, which is right here. Once the waypoint is reached, the robot will just simply turn back and go to the waypoint on the first side of the water tank.
Right, so that was the video. Hopefully now we have a better idea of how the experiment looked like. So now I want to present the approach we took to provide the multi-agent system. So here you can see we have the camera that's above the water tank. And the camera provides, after we parse the images, we have XY coordinates and orientation. I would just refer to it as a pose, because position and orientation makes a pose of the robot. Then we have a collection agent, and the collection agent basically filters the output from the camera, does some averaging and smoothing, and then sends the pose estimate to the controller agent. The controller agent has the subsumption architecture in it and determines what kind of control inputs, delta and omega, it sends to the vehicle. And the control agent also checks if it arrived at a waypoint yet, and if it did, it requests a new waypoint from the strategy agent that provides the new waypoint to go to. Then I have a monitor agent that monitors the behavior of the vehicle, and then if there's a suspicion for a poor performance, then it requests the diagnostic agent to run diagnostics. And
So this is everything on your laptop, right? And then laptop sends some signals to your vehicle, right?
yeah, but without the loss of generalization, you can run the same code on the computer, on the actual robot.
Can you?
Yes. It's not computationally intense, like.
But vision must be on your laptop.
Yes, vision is on the laptop.
Yeah, okay.
And the motivation is like, in the future I would have some other sensors on the robot that can determine the position and orientation, but I probably wouldn't use the camera in that case. And then the diagnostic agent runs the diagnostics and determines if a fault happened, and if it did, it takes certain actions. So now, just briefly about scheduling, the whole system is event-driven, so I don't have a set timer or set frequency I'm running these agents. It's purely based on the events that happen. An event can be a new pose estimate is available, or the robot achieved a waypoint, and so that's another event. And then I can dynamically rearrange the agents and step them in a sequence. So the control agent, we have 2 actuators and 4 control inputs. And because we have 2 actuators and 3 degrees of freedom, it's an under-actuated vehicle, which makes it a more complicated control problem. And hence I have delta and omega for each of the wings. I have these 4 primitive motions I can achieve with this vehicle. And it's moving forward, turning left, turning right, and then doing nothing. And I know that if I want to move forward, I have to have the symmetric delta shift in both wings. I produce the force in the same direction, and I just go forward. And if I want to turn, I have to do it in opposite way, so it turns around its own axis. And at this point, I know direction, but I don't know what's the exact value of the delta or the omega, because that depends on the individual robot and it can change in between them. So I will have to have some kind of learning algorithm to be able to determine these numbers. And also, just a note, the faster frequency means that I'm performing the move faster. I'm generating more force, but it doesn't, the frequency itself, the wing beating frequency itself doesn't change the direction. And this is the rule base for the subsumption architecture. Basically, the higher number the layer has, the higher priority it has. So in this simple case, if true, then idle, just do nothing. But then I have this set of rules. If heading left from my desired direction, you want to turn right. If you're heading too much right, you want to turn left. And if you're heading straight at a waypoint, then move forward to get closer to the waypoint.
And who gives waypoints?
Sorry?
They are on the waypoints. They are on the list. That.
Yeah. The strategy
Okay.
agent has a list. It's like
Okay.
a
Okay.
pre-computed list of waypoints.
Okay, so it's not adapted. It is fixed.
Yeah, it's fixed
Okay.
at compilation time. And then if I reach a waypoint, I want to get a new waypoint. And if I'm outside certain perimeter, I want to turn right to avoid going even further.
Can I
And
ask, on the
yeah.
controller agent, is it a straightforward generalization to 6 degrees of freedom? Like here you're just doing 3 degrees.
Oh yeah. So this is for the 3 degrees of freedom case.
Is it pretty easy to generalize to 6?
Yeah. I have a point about it later that it can be
Sorry.
generalized.
Okay.
No, you're good. So monitor agent, it monitors the performance of the vehicle, and basically the idea here is I have some expected behavior. Let's say I know if you turn, it should take certain time, and if it doesn't, or if it takes longer than expected, then you should start diagnostics. And then this is applied for the diagnostics agent, where, as I said, I know if I tell the vehicle to do certain maneuver, let's say turn around, I know how much this normally takes, and if it takes significantly longer, I assume it doesn't take any shorter, then I know that something's wrong and I have to take action. And basically, the idea here is I have some normal distribution of times that it takes to perform the maneuver, and then I have certain, let's say, one standard deviation of each side, and that's my range I accept. And if I'm past that point, I can tell that most likely I'm not in a good operation condition. There's some fault happen, and this will get more clear with actual numbers. So I will revisit the idea later with actual measurements, so it will make more sense. As I mentioned, because we don't know a priori what kind of control parameters we need to use, I need some kind of initial learning. That's where I will use the evolution algorithms to be able to learn for each vehicle. Because each robot is different, because of manufacturing differences, nonlinearities, and so on. So before I can go and fly, I need to know these control values. And then in flight, if a fault happens, I want to be able to update these control values so I restore certain functionality.
So you're using evolution strategy, right? You are not using crossover.
I'm using evolution strategy.
Yeah. Okay.
Yeah. So the initial learning, I'm using extrinsic and intrinsic evolution. I will explain it later. And I'm using evolution strategy, and yeah, so the initial values I use extrinsic evolution to evaluate that my algorithm works, and then I use the intrinsic evolution on the actual hardware to get the numbers specific for the given robot. And once all these numbers are evolved, I can start with the trajectory following. So again, this is for the in-flight learning. If I do a specific movement and the performance is not sufficient, I run the diagnostics, and if I see that if my likelihood function triggers a fault, I will need to adapt the rule base. And the way this works, I know in advance what kind of faults I can recover from. Let's say if my battery is dead, there's not much I can do. But if I have, for example, a damaged wing, then I can recover from that up to a point.
So you have fixed rules.
Yes,
How
I
to
know
adapt
what
the
kind
rule
of
base.
faults
Okay.
I can recover from.
Okay.
And the assumption is I have only one fault happening at a time, and first of all, I need to inject this fault I'm trying to recover from. I do it in experiment in controlled environment, and then I measure the response, and then I evolve the new control parameters so I can restore the performance. Again, this will become more clear with an actual example. And this is just once over the same. If I have a specific fault that happened, I can adapt the rule base and then recover from the fault. So now the results. I will go over initial learning, waypoint following, fault detection and recovery, and obstacle avoidance. So for the initial learning, I needed to verify that the evolution strategy is a good choice for the learning algorithm. And because I had access to a simulator developed by a third party, but the simulator was for a different vehicle than ours. So the values that we would learn from the simulator were not very applicable for our case. So I instead made this very simple fitness function that basically says the fitness is proportional, like the higher fitness is, the shorter time it takes to finish the movement, and the movement will be finished faster if I produced more lift. So that can translate directly to the higher omega is, the higher wing beating frequency, and the higher the delta shift is, then I get more stronger control action. And that's basically what I'm looking for, because that will translate into a shorter time. And I know that these weights, this KL, KR, basically if I keep them at 1, that means move forward, and if they have opposite signs, it's for the turning maneuver. So this is how I was able to verify that the evolution strategy indeed converges and finds good solution. For the intrinsic evolution, I again know that the fitness is proportional, inversely proportional to time. So that means the shorter time, the higher fitness, because I want to find a solution that lets me do the maneuvers quickly. So in this case, for turning left and right, time needed to turn around by 360 degrees. And to move forward, I actually set a waypoint. Let's say be easier to show. So I have the robot right here, and this is a waypoint I want to go to, right? And so I'm measuring the time it takes to go to the waypoint, but because I'm expecting it will be hard for the robot to actually reach the waypoint exactly, I'm checking the time it crosses this coordinate, this y coordinate of the waypoint. So if the robot gets here, let's say, this is my time, and then I measure my distance from the actual x coordinate I want to be at. And that way, and then I have some weight, alpha, beta, that tells me, that's basically a scaling factor, to tell me, the offset from pixels to the seconds, so I can scale the different units. And that gives me the fitness for the move forward. So here's some results. Basically, the takeaway here is on the left, we have the extrinsic evolution, several runs for 20 generations. And I can see these are 4 turns left and right. I can see that in almost all cases, I reach the global optimum, which in this case is 600, before 20 generations. So what I'm evaluating here is I want to see that if I use 20 generations, it is very likely that I find a good solution within those 20 generations. And then here we have intrinsic evolution on the right for left and right turn. And here I'm using time instead of fitness because it's more, it's easy to visualize how I'm decreasing time and improving my solution during the generations. And so basically we're starting at some randomly initialized value, and then we improving the time as the generations continue. until I reach some good solution.
But
And
this is turn right by which angle?
360 degrees. You want to turn
Oh, I
around
see. Okay,
because
okay,
that's easy to
yeah,
measure.
Okay.
And the interesting thing here is that it can happen that, for example, here, this 14th generation, if I find, as I'm producing the offsprings, the new generation of solutions, it can happen that I produce actually worse solutions than I had before. So in that case, I'm keeping the fittest individual so far, and continuing with the evolution. And only if I find somebody better, then I will update my best solution. So you can see here that probably the best solution was found on 14th generation, and since then, no improvement was made. And here, this is
Can I
for
ask?
yes.
On the previous slide, so I guess two questions. One, is it just because of the randomness in initialization that right is improves more than left turning?
You mean for the intrinsic evolution?
Yes.
Yeah.
Is it just because of?
Why is there difference between red and blue?
Yeah.
So there are two explanations, two factors. One is random initialization.
Okay.
So it's possible that it was different value in the beginning. And also, we don't expect the times to be the same because the robot may be a little bit off center, one wing performs better than the other one.
But basically the wings are the same in this case.
Well, we assume they're the same,
Yeah,
but
okay, yeah.
practically
Yeah.
they perform differently.
The wings are, but the linkages may
Yeah,
not.
yeah.
There
Yeah.
might be different friction, and
Mhm.
so it's not perfectly symmetrical.
And quickly, what are on the left-hand side? What are the units for fitness? Like, what is maximum 600 mean?
Okay, so I had this was the fitness function I used, and basically I know that I have hardware limitations for the delta and omega values.
Oh, okay.
And so then when I multiplied it all together, like the best number I could reach to was 600.
So there on the left, you could have red and blue curves as well, is that right?
Yes, I just mixed them all together.
Okay, but would you see the same differences like with on the right? Or did you see that?
So I would not see the differences here because in my simple model,
Yeah.
they both behave the same.
Okay.
Only difference would be like the initialization values. You can see there's more spread on the axis. All right. So for the move forward, actually what happened was that into 20 generations, you can see this is the initial position, and this is the waypoint. So the idea was I go forward, I reach the waypoint, and calculate the time for that. But in those 20 generations, basically only one solution reached the waypoint. All the other solutions kept spinning or diverged. So then I stopped the experiment after a certain time because it was obvious that the robot is not moving in the right direction. So basically for move forward, only one solution was found, and so I used that solution. And I should also mention, you might be asking why only 20 generations, if typically I would run the algorithm for several runs, let's say 20 generations, but I would run it like 100 times to find the best solution. So here I was limited by hardware because it's all 3D printed plastic linkages, and the whole assembly is fairly delicate. So if I would run it more than that, if I try to, let's say, repeat the whole process, I could run into the problem that the hardware would break, and I would have to replace the components, and then would have to start from scratch, because then suddenly the numbers wouldn't be working on the new, it would be essentially a new robot. So I was limited, I was like looking for a compromise between how precise I can evolve for how long, and also for how much the hardware can last. So these are the initial control parameters. Basically on the left, those are the extrinsically evolved. Again, this is not surprising that I use the highest possible wing flapping
So
frequency.
these data are evolved.
Yes, this is
And
evolved.
they were repeated many times and averaged, or just one?
Just the best.
I see.
And you can see here that basically whatever were the hardware limits, this was the algorithm found the best solution, which is maybe not that surprising, but it's like reassuring that I know that the evolution strategy, the way I set it up, can find in 20 generations a reasonably good solution. Then on the right, I'm using the intrinsic evolution on the actual hardware, and the highlighted are the changes. And so you can see, for example, for right turn here, instead of 30 radians per second, I have 25, and then I have 12 here, which is somewhat surprising. The basic idea says it's better to turn right using only one wing instead of using both wings.
Isn't this result on the left kind of too good? Because I understand that it must be 10 and 10 or minus 10 and 10. But white is always 30. It can be 29, for instance.
I used the best solution that I got from all these like 100 runs. Like if you go back, like I did all these runs and got the best solution.
I see.
And you can see that basically whenever I reach 600, that basically represents my optimal solution, like a global optimum. So yes, arguably it's not very precise because the model was very simple. The fitness function was kind of very simplistic, but my intention was to see if I can get good results within the given time frame. So I was intentionally making a simple model, because then I would use the intrinsic evolution to test the actual robot and then get the relevant numbers. So you can see, yeah, and this is, so basically from the intrinsic evolution, it turned out that it's better to turn only using one wing instead of two at the same time. And for going forward, I had different setup for the delta shift and for the omega. And these are the values I used for in the next slides. So for waypoint following, I have two control values, and I set up two waypoints, and I will go back and forth between them. And I want to see how well the robot will do. So this is, so you can see here the blue is the waypoint I'm going to, the green dot is the robot itself. And I'm starting here. I started with the robot facing forward and the waypoint being behind it to make it kind of harder. So the robot had to turn around and then go towards this waypoint. Then as I reached the waypoint, I requested a new one, turned around, go to new waypoint, and when I reached it, I went back. And I did it a couple of times. This is the trajectory, you can see. We have the two waypoints here, and we can see that the robot can fairly accurately follow the trajectory and go more or less directly to the waypoint. And just to give you a sense of how fast / slow the robot is, this is 6 times sped up. And you can see, so like I started up, the waypoint is right here, it's behind the robot, just to turn around and go towards it. And since this is 6 times faster than normally, so you imagine this is like 2 minutes long video, normally it would be like 20 minutes to perform the whole experiment like this.
This is a really sluggish system.
Yep. And like a side note, this is like a second generation. The first generation was even bigger and slower than this one. So I had to do some improvements to make it faster, but it's still, this is the.
Is the flapping so different because one of those wings is trimmed on this one?
No, these are the same wings.
Okay.
And I suspect it's just the frame rate of the camera, and they have like different frequencies, and then you speed it up, so. It makes all these effects. Like in fact now the right wing is moving faster, except it's just kind of, yeah. It's like if you're looking at like propellers on a video.
Yeah. It's precession.
Yeah.
So similar.
Yeah. So basically, yeah, you can see here it goes back and forth. It follows the trajectory, and I just had to do it for a while.
Is it getting tired now?
It had battery for like 20 minutes, so like this was like a one run, and it was ready to be recharged. All right. So this is just the control inputs, delta, omega, as I was changing them, and then these are the rules that were fired at the given point. So you can see there's like fairly, we can maybe say it's kind of more heavily on the turn right side, which may reflect that the parameters I found are not optimal, they're just reasonably good, and that maybe turning right is taking longer time than turning left. Here you can see the orientation. We have a wraparound around 180 degrees. These are those big spikes. They correspond to basically when the robot turns around and goes the other direction. And so you can see I maintain the heading around 10, like 0-ish degrees, and this is around 180 as I'm going back. So this basically shows me, this reflects the sort of straight trajectory between the waypoints. And here you can see the angular rates, and all the time in between, well within like 10 degrees per second. So this shows you that it's like 36 seconds to turn around, which gives you another insight in how slow is the system. So just summary for this, I would say the waypoint following is reasonably good for our application, and we can easily extend it to multiple waypoints. You can basically make arbitrary trajectory just by adding waypoints. And I wasn't addressing the problem of trajectory generation or some kind of path planning. That would be a different story. But we definitely can follow the waypoints, and just between those two waypoints, just go from A to B. It takes around 5 minutes. So just to get some insight into how long the whole experiment takes. So the next thing I want to talk about is fault recovery. Basically, as I mentioned before, we inject a fault, measure the response, evolve new values of the control parameters, and then save it for the later application. So I did left wing damage. So I cut off a little bit of left wing, and the assumption is here the right turn will be most affected, as well as going forward, but the right turn will be most obvious, because the left wing basically does all the work when you're turning right. So if the wing is damaged, then I will notice it. So what I did is I then run again the intrinsic evolution with the damaged robot, and I was able to get new values for right turn, even left turn, and move forward. These are updated. You can notice before this was 25, now it's 30, and that's the hardware limitation.
This is from intrinsic or extrinsic?
This is intrinsic. This is on the actual hardware.
Okay.
And so here the idea for diagnostics is after startup, I initiate turning right, I measure the time, and if it's more than some Tmax that I determine based on my data, then I have a fault present. In this case, it's the left wing damaged, and I need to upload my control inputs. So this is, on the left, is a histogram of my turn right times I measured with the original robot. So you can see average was around 77 seconds to turn around, and I fitted a normal distribution over it, and so what I chose was to do one sigma interval on each side, which goes from some 61 to around 94 seconds would be the 68% confidence that this is a good behavior. And so basically I said if the turn takes more than 94 seconds, I consider it as faulty because it's beyond my confidence margin. And here you can see this is a box plot, so we have median, and we have this between 25th and 75th percentile spread. This is how much it took us to turn right with the original robot. This is how much it took when the wings were damaged, but we still had the original control inputs. you can see the increase from like 77 to like 110 seconds. And then after I recovered using the newly evolved control inputs, I'm getting back or closer, reasonably close to the original performance. Any questions about this? All right. So just to show you a quick video here. So what happens here, after I initialize, I say turn around, and I measure the time it takes, as I mentioned. And once this happens, I will do all the comparison and calculation and update of the control values, and then I will follow, because now it already detected a fault, recovered from a fault, and is moving towards a waypoint. And this is the trajectory we just saw in the video. Just quick summary. We tested left wing damage. The original degradation performance was around 40%, and we were able to recover comparably good performance. And this can be extended to other faults, right wing damaged or similar. And the last thing, just really quick, obstacle avoidance. Basically what happened during experiments, that often the vehicle just goes to the wall. And say it turned out that simple turn right doesn't prevent it, because the robot has momentum, so if you just turn right, it still has the momentum and moves forward. So one way to avoid that would be to restrict the area and say don't go beyond some boundary within the water tank. But that would be impractical because it's already on the limit, I would say. It would be nice to have even bigger water tank to be able to do more maneuvers, but we didn't have that. So what I decided was to improve the obstacle avoidance routine to be able to somehow anticipate the wall, the collision, and avoid that. So this is the original rule base. Here it says if outside perimeter, hard turn right. So that didn't work so well. Instead, I'm saying if obstacle ahead, then I would avoid the obstacle. And let's say the obstacle would be some kind of virtual wall in the middle of the water tank. This is the algorithm. I'll just skip it for time reason, but then I can get to it later. But the idea here is I have an obstacle I know about, and I'm able to move around the obstacle and still finish reach the waypoint I desire. Again, just a quick video to, this is, yes. So I start from the beginning. It sees the obstacle. I'm not dealing with the problem of detection. I just assume the robot knows where the obstacle is. And it uses intermittent waypoints. So basically, I know what was the line between my original waypoints, and I move these intermittent waypoints around the obstacle. Basically, I move it around until I'm sufficiently...
It knows the obstacle. It means the camera sends him his XY coordinates and orientation, right?
Yes, yes,
Okay.
I know it from the camera.
Being close to the obstacle.
So the robot itself can calculate, its relative...
But all information comes from the camera.
Yes.
Okay.
Yeah, so and then it turns around and follows to the waypoint. So yeah, so I said obstacle detection is a separate problem. I just assume I know where the obstacle now is. So just to summarize, initial learning to be able to get the control parameters before we can perform any other experiment. Waypoint following, we can use arbitrary trajectories, basically any number of waypoints you can follow at with 2. Fault detection and recovery demonstrated with one wing damaged, and obstacle avoidance, we can avoid an obstacle within the area, but it would be good to have further improvements to avoid the walls and so on. So any questions before I go to conclusion? Yes?
Well, so I guess one question, I think I missed it, but with the controller for when it's have no fault.
Mm-hmm.
You didn't do adaptive control where it switches over to the fault controller, does it?
So the adaptation here happens in the fact that I'm switching the control values I have associated with each movement.
Okay.
So I have these like four basic movements.
Right.
And then I know that for each individual fault, I would use this updated value that represents, like different omega and delta
Right.
for a given movement.
Right, but it wasn't like in the beginning you showed like this layered control architecture. It wasn't
Mhm.
like that, like you didn't have like one of the layers be a fault handler, like it detects it.
So no, so the subsumption, the layers were for determining where to go,
Right.
but then I have separate agent that updates, that handles this kind of fault behavior.
Oh, okay, okay.
So then the subsumption architecture itself would not be changed by a fault.
Got it. Okay.
All right, so these are the research outcomes we defined at the beginning, and I'll just address each of them individually. So first, understanding if it's even viable to use a multi-agent system for a flapping wing vehicle. So yes, it is a suitable solution for control of such a robot. And the benefit is we don't need an identified model. We don't need a model of the robot, which is often hard to get as we get into smaller scales. We need more precise measurements. That's involve, complex aerodynamics and so on. So that makes it easier to use if you don't need a model. And then we used evolution algorithm to be able to find a good control values instead of without the model. We basically evolved it on the actual hardware, so we didn't need much a priori information. Then developing a multi-agent control system, allowing us to follow trajectory. So to our knowledge, multi-agent system has not been used for a control of flapping wing robot before. The important part is here this system can be used on other flapping wing robots. It can be easily extended as you asked before, basically for full 6 degrees of freedom, except in this case I would have more, like the rule base would be longer because I would have to maintain the altitude, we have to maintain the heading, and that would get more complex, but the basic principle would be the same. And also this system could be extended and used on different kind of robots, not only flapping wings, but walking robots would be a natural extension because there you also benefit from not having a model and using the evolution algorithm to evolve to find a good motion for the given movements. Because the code is publicly available, other people can use it and get a jump start on their projects.
We will use it. We'll use it in my class definitely next quarter.
That's good. And as I said, we can adapt the rule base to add more. The subsumption architecture can be extended again to do even more tasks than simple control and trajectory following. We can have another layers for target identification. Swarming would be another interesting approach. Autonomous return to the base and so on. Developing fault detection and fault recovery mechanism. So that's part of the system, as I demonstrated. We tested it with wing damage fault. It can be extended to other faults too, given the hardware improves too. Because right now we don't have any redundancy systems built in or any additional sensors, which would be like a prerequisite for some other, let's say, power system failure or other types of fault. And again, just overarching goal, we developed a robot that can follow a trajectory, which is part of our autonomous requirements. We have fault recovery procedures, and on top of that, we have obstacle avoidance feature. So that is just this is available. It's like parts of the robot are 3D printed, so that's fairly easy to produce it on like a broader scale. and it's all available online. And if this is like a fun slide, if like I had time and resources to like extend this work, I guess the first thing would be to improve the hardware to be able to produce enough lift and to take off. Then naturally extending the multi-agent system to full 6 degrees of freedom, and possibly incorporate more sensors and navigation algorithms, and then extend the autonomy to be, swarming or whatever is desirable. And I have 2 relevant publications. One is a conference proceedings, and one is a journal article, fairly recent, which the copies should be. You got them, yes. So with this, I'm up for questions.
I have just one question. I already asked you many questions earlier, and last time when we met. So when we submit papers to like machine learning journal or robotics journal, there's usually a complaint that we don't have enough statistical evidence. What is the evaluation methodology? And your evaluation methodology is kind of strange because you are just selecting the best result. Usually they don't like it. They usually want to have some statistical data of all your runs. The reviewers didn't complain about this, that you are selecting the best result?
They had some comments, but I don't think they touched the experimental data. So
because it is not standard strategy to evaluate results in machine learning.
sure, I mean, like, are you pointing to some like specific best case scenario, or I mean, like, yeah. So like for the journal paper, they had some comments, but they didn't have comments about the methodology itself necessarily.
It wasn't enough to reject it.
Yeah, you can, I guess.
That was the bottom line.
Uh-huh.
I have a question.
Yes.
Regarding your results with the intrinsic evolution, there was a question about why does the red one is the left wing, and why does it get stuck on that
Yes.
one? But I was wondering, was that related to how you create your layer? It might be that because each layer have priority over the layer before that. If it's arranged such that the right wing has more always have more priority somehow, maybe that affects the results of your intrinsic evaluation or evolution. Maybe.
So for this initial learning, like I basically fixed the rule that I was doing.
Yeah.
So there was no like if you let's go back to. Yeah, here. So basically,
turning left and right. Sorry.
was that?
Turning left and right, not the wings.
Yeah. So if I'm turning left, I basically commanded the robot to just turn left and do nothing else. And the same if I was turning right. So there was like the subsumption architecture was not, the layers were not like doing anything. It was like fixed to a specific. Yeah.
So you mentioned, so this is the first application of using multi-agent systems for micro flapping and
Yes.
But using evolutionary algorithms is kind of orthogonal to the multi-agent system. Right? And so is there other work about applying evolutionary algorithms for micro flapping wing vehicles?
So there is definitely workable like evolvable hardware, like, but that's kind of separate thing. The other lab that was like involved in this project, they were more interested in evolving the actual motor controller. So like not saying where to go, but actually like controlling the waveform of the wings and recovering from faults in that way. And I cannot think on top of my head if people used it for like a control of the robot. So yeah, I would have to look into it.
Or like, do you know offhand, like what a controller approach did the MIT lab do with their micro air vehicles?
Oh, so I know for the RoboBees, for the tiny ones, I think it's MIT or Harvard, they use the classical control.
Okay.
And they were like, and they have all these like devices to like measure all the parameters on the model, develop some kind of controller, even like they had some adaptive control and so on. But yeah, so I would say classical approach.
Would you say that your contributions are more a development of theory or more development of practical advances, engineering type advances?
I would say this is definitely more like the practical engineering side. And with that goes the reusability and like applicability for like other projects and other robots and so on.
Good question. For the fault detection, you would have to go through and collect data for every potential type of fault and then input it after for it to be able to detect that fault in real time?
Yes.
Okay.
The general concept behind that is usually on fault recovery, you can't accommodate every fault.
Right.
So what you do is take a small set of the most catastrophic ones, and that's what you develop a fault recovery mechanism for. So on this one, what we decided is, well, we just want to illustrate the concept. So we'll just do one, a damaged left wing. I mean, we could have done 2 damaged wings, stuck linkage, you know, all kinds of things, but we just picked one for a proof of concept that, hey, we can evolve a recovery mechanism, a different set of table values for deltas and omegas, and when we detect that fault, swap to the new table, we can recover from that particular fault.
Would you call is the subsumption architecture well suited for learning, particularly more autonomous kinds of learning, so that it's not learned in the lab, but it's actually learning a new motion, a
new behavior?
Yeah, a new behavior, something like that. Is a subsumption architecture a good place to think about that, or is that actually much better for just creating rules that you develop in the lab, basically, and putting them in a really good, fast, efficient tiny bits of code?
So you can certainly have like dynamic subsumption architecture that's like a natural extension that you basically adapt your rule base based on a situation or some kind of external event. And so I would imagine this would be related. Let's say if you have multiple robots and they're trying to learn some kind of behavior, this would be a way to go potentially.
If I may comment, I think that would be interesting if subsumption. To me, the key idea there is that the priorities, there are layers that are more important that can subsume the other layers. So that can be learned. That you can apply machine learning things for the robot to learn which task should be more important than the other.
So to change the priority, maybe.
Maybe, yeah.
Interesting.
Yeah, on this one, we just, this is our priorities.
Sure.
But maybe that's not the right priorities. So yeah, that, in addition to adapting the values, you could do the perturbation of which rule fits into what layer.
And you might have to have, a set of task or behavior at a certain level, and that you can swap in and out of, but it stays in within that level or some sort. Maybe, I don't know.
You know, to do that sort of thing would suggest that would be best evolved extrinsically. But as Michael pointed out, trying to get a decent model on these things is so difficult.
Sure.
That you would have to have a decent model to do that, and then verify it, and that could give you like the initial population for an intrinsic evolution and verify it on the actual hardware, because it's probably going to be subject to a little bit of change because of variations in manufacturing.
Have you tried other types of agent-based models? For example, what you had is that basically you had a very predefined list of agents, heterogeneous agents that offered a specific task. Have you tried homogeneous agents that basically the functionality evolves out of their interaction, so you apply the input data somehow and then you always get different interactions between the agents, right? And then from that you derive your motion control, for example. So it probably goes more towards neural networks or recurrent neural networks. Do you try anything like that? And I'm wondering if, for example, if you would like to expand your model, how easily is it? Can you scale it up? Can you expand it if you're working on a very specific list of agents? If you want to include a little bit different functionality, is that easy? Or would it be easier if you have a homogeneous set of agents, or just slightly varying, but where the functionality evolves out of the activity, how they interact with each other?
Because you're talking more like you have like some kind of, let's say, cooperative number of agents, and then together would like come up with some control strategy, essentially, which could be interesting for, let's say, like very like adaptive model for different robots or different systems. You have this kind of framework you can work on. Our approach was more like we had this like specific problem, and it was basically like how we can best address this problem is like this like given set of agents. So I did not test the like other types of agents, but I can imagine it would be interesting application.
Because on another level, right, you would employ your little flying robots in exactly that way. Once you have 1,000 of them, and they're supposed to solve a certain task, then they're exactly performing this type of agent-based system too.
And then you get into the whole like swarming idea, and you have like cooperative or like competitive swarms, and we get some kind of emerging behavior from that.
Yes.
But ultimately, for all application, you need cameras on the robot, right?
It would be helpful to have cameras, but yeah, I guess the sensors issue. Yeah, some kind of vision-based sensors, or you could.
Super miniature GPS units that are really accurate.
Well, one of the things that we were collaborating with some people back at Wright State University, and one of the things that they were suggesting is to have something like a transponder. And you could mount that like at two corners of the tank, and then you could ping those to figure out where you are, as opposed to using
Sonar.
the camera with the colored dots, and then you can figure out your orientation and everything. You could use transponders that are mounted on the corners of the tank to determine where you are in your orientation. In practice, you probably use some sort of proximity sensor or whatever to tell if you're next to a wall or something like that. But that the camera was relatively inexpensive, and at least it would give you some idea of where you were.
But I think this technology will be practical, assuming that you have very many of those devices, right?
Yeah.
They always work in big groups, like hundreds, thousands.
Yeah.
And the fault tolerance is you can lose a few of them.
Yeah.
And that goes like mass scale, so you don't like really care if you lose a few of them.
Well, the idea of having those little small ones is they're literally throwaway.
Yeah.
Spend a few bucks to buy each one, so what if you lose 20% of them? No big deal.
This idea of evolving, instead of giving it a complete program, what if there were just bits of logic that it could use, and it could decide how to assemble them, and see if something worked better than what you thought of as a designer? It'd be interesting to play with that idea.
Might be another project. Follow up.
Any other questions? Okay, well, thank you for coming. If the committee could just remain here with Michael, and we'll take a 2-minute break so you can recover or something. And then okay.
You want to turn off the sending unit there?
Yeah, I'm gonna switch off the stream. This is the public part is over. Okay.